Hello everyone, this is the fifth lecture. Recall that we looked at many examples of unconstrained optimization problem in the last lecture and have also started with the constrained optimization setup. Okay. So, yeah, when you look at the constraint setup that we had in the last lecture, right. So, yeah, we wanted to minimize f of x subject to some set S, okay, and that set is not any set, but a set described by P inequality constraints and M equality constraints. We also looked at an example, the utility maximization example that we started with in the very first lecture. Okay. So, yeah, let us first understand how to construct a general solution. Okay. So, yeah, we have this particular problem when f of x subject to g I of x less than or equal to 0 for all I equal to 1 to p, and h j of x equal to 0 for all j equal to 1 to m. Okay. We first construct something called as the Lagrangian. Okay. So, let us assume that f is a function from Rn to R. So, that means x is a vector x1 dot dot xn. So, L is actually a function of the x vector and certain vectors called the Lagrange multipliers for inequality constraints lambda 1 to lambda p, and the Lagrange multipliers for equality constraints, which is mu 1 to mu m. Okay. So, yeah, Lagrangian is a function of x, lambda and p. So, there are total of n plus p plus mu n plus p plus m variables. Okay. So, what is the expression? It is f of x plus summation lambda I g I of x I equal to 1 to p plus summation mu j h j of x, where j goes from j 1 to m. Okay. So, this is what we call as the Lagrangian function. Okay. So, this is a new function that I have constructed. So, we have f the function f, which was only a function of x, the functions g I and h j, right. So, they are also only functions of x. Okay. But the Lagrangian that we have defined here, that is actually a function of x vector, lambda vector and the mu vector, and it is defined as f of x plus summation lambda I g I plus summation mu j h j. Okay. So, all right, why did we define this? So, we are actually going to now find the set of critical points. Okay. So, the step 1 in any solution finding in optimization is to find the set of critical points. Okay. But how do you characterize the set of critical points? It is the set of points that satisfy the following set of constraints. What are they? So, take the gradient of L with respect to x, okay, and equate it to 0. Okay. So, this will give you n constraints. Okay. So, the x, lambda and mu that we are going to find should satisfy this constraint, that is, when you take the Lagrangian, when you take the gradient of the Lagrangian only with respect to the x variables, right. So, that must be equal to 0. Okay. And so, yeah, this actually means that the following must be satisfied: del f of x plus summation lambda I del g I of x plus summation j equal to 1 to m mu j del hij of x. Okay. You must be able to give x lambda i's and mu j's in such a way that this quantity this vector is actually equal to the 0 vector, that is the first step. Okay. But yeah, you have further more constraints to be satisfied. So, the x that you give must satisfy this constraint hij of x equal to 0 for all j equal to 1 to m, of course. So, if the constraints are not satisfied, then the point that you have constructed is not in the constraint set, right. So, yeah, that needs to be satisfied. The other constraint is a little tricky. So, you need g I of x less than or equal to 0, that is fine, but other than that you need lambda I g I of x to be 0 and lambda I to be greater than or equal to 0 for all I equal to 1 to p. Okay. So, these set of constraints that we have defined, right, these are called as the Karush-Kuhn-Tucker conditions, or in short called as the KKT conditions. KKT stands for Karush-Kuhn-Tucker. Okay. So, the set of points x lambda and mu that satisfy the Karush-Kuhn-Tucker conditions. Okay. So, that will form the set of critical points. Okay. Of course, it does not stop there, okay, as you should have guessed by now. Okay. We also, after finding the set of critical points, we look at the second order conditions. Okay. So, what are the second order conditions? So, first we look at the set of active constraints. So, what are the set of active inequality constraints rather? Active constraint set. So, let me call that I. So, that is I such that g I of x star is equal to 0. Okay, I will also call it I of x star since it varies with respect to x star. Okay. So, yeah, you can see that the critical point x star may satisfy this particular constraint g I of x either with equality or it could be strictly less than 0. So, we could have g I of x star equal to 0 or we could have g I of x star strictly less than 0. So, we pick those set of constraints from 1 to dot 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 p for which g I of x star is equal to 0. So, those constraints are called active constraints, okay, and the others are called inactive constraints basically. Okay. So, fine. So, you will see why the set of active constraints is needed shortly. Okay. Now, I am going to construct a set, okay, so called as the tangent space. So, the tangent space T is the set of all directions that satisfy d transpose del h j of x star equal to 0 for all j and d transpose del g I of x star equal to 0 for all I in I of x star. Not all I, but only those that are in the active set I of x star. Okay. Now, we have a similar set of conditions like what we had in the constrained optimization, sorry, unconstrained optimization. Okay. So, if T trans, sorry, I will write it as D since I wrote D here. T transpose del 2 f of x star T is greater than 0 for all T in T of x star, then x star is local min. Okay. And the constraints will be similar. Okay. So, I will just write them down anyway. If T transpose del 2 f of x star T is greater than 0 for all T in T of x star. Okay. So, did I sorry, this is less than 0. Then x star is local max. If there exists T1 such that T1 transpose del 2 f of x star T1 greater than 0 and there exists T2 such that T2 transpose del 2 f of x star T2 less than 0, then x star is saddle point. And finally, if there exists T such that T transpose del 2 f of x star T, okay, I should have written T1 in T of x star. Okay, can correct it quickly. T1 in T of x star such that this, and T2 in T of x star such that, and T in T of x star such that T transpose delta f of x star T is equal to 0, then further probe needed. Okay. So, yeah, at least second order conditions in constrained optimizations is quite difficult to verify analytically in practice, but the only thing that you need to note is that the difference between the conditions that you saw here, okay, what you had for unconstrained optimization and the ones that you are having for constrained optimization is that here you are actually considering every non-zero t, right, or yeah, sometimes the zeros as well if required, right. But here you are considering t, I mean only those vectors t that are in the tangent space T of x star. Okay. You do not need to consider the other directions. Okay. So, if that happens for this restricted set of vectors, if you have the condition T transpose delta f of x star T is positive, then x star is a local min. If it is less than 0, then it is a local max. If you have one T1 in T of x star such that the quantity is greater than 0 and T2 in T of x star such that the quantity is less than 0, then it is a saddle point. And if you have one T for which T transpose delta f of x star T is equal to 0 in T of x star, then further probe will be needed. Okay. So, yeah, I mean you can see that yeah, these are harder constraints to verify, but nevertheless I mean, so I am giving this for the completeness of analysis. Okay. Given that we have characterized the solutions, right, we will now look at an example. Okay. So, let us consider the same example that we had given. We are minimizing, so we just wrote a general utility function. So, we will consider minimizing minus x1 x2 subject to the condition that p1 x1 plus p2 x2 minus w less than or equal to 0, minus x1 less than or equal to 0 and minus x2 less than or equal to 0. Okay. So, if you actually plot this, okay, I mean, so to see what this constraint set actually means, right. So, you will get the following set. So, this line is I can extend it fully, but since this is only relevant I have stopped it here as a line segment. So, this is p1 x1 plus p2 x2 minus w equal to 0. Okay. So, that is this line. Okay. So, since we want this to be less than or equal to 0. So, we are considering this region, and so this is x2 equal to 0 and so this is x1 equal to 0. So, since you want x2 greater than or equal to 0 or minus x1 less than or equal to 0. So, you consider the intersection of all these 3 sets, you will actually get this particular set what I have drawn here. Okay. And so, x1 and x2 can take values only in this particular set, the shaded region in the figure here. Okay. And you are expected to minimize minus x1 x2 or maximize x1 into x2. Okay. So, let us find out with the theory whatever we have developed until now. Okay. Okay, there is a minor modification in whatever I have written down. I should have actually written del 2 L of x. So, I am sorry about this. So, I have to consider the Hessian of the Lagrangian function defined here and not the f function that has been written here. So, that needs to be modified. Okay. Let me modify it everywhere. Yeah. All right. So, fine. So, let us first, so if you recall what we need to do, you first need to construct the Lagrangian, as simple as that. So, that is L of x1 x2, and you have 3 inequality constraints and no equality constraints. So, you have lambda 1, lambda 2, lambda 3, and the function is minus x1 x2 plus lambda 1 into p1 x1 plus p2 x2 minus w minus lambda 2 x1 minus lambda 3 x2. Okay. So, this is basically the Lagrangian function. Now, we will find out the points that satisfy the KKT conditions or the critical points. Okay. So, we have del x L of x lambda equal to 0, which means, so when you differentiate this with respect to x1, you have minus x2 plus lambda 1 p1 minus lambda 2 equal to 0, and if you differentiate with respect to x2, you have minus x1 plus lambda 2 p2 minus lambda 1 p2 minus lambda 3 equal to 0. Okay, so, that is the first set of conditions. The other set of conditions are you have so p1 x1 plus p2 x2 minus w less than or equal to 0, lambda 1 into p1 x1 plus p2 x2 minus w equal to 0, and lambda 1 greater than or equal to 0. Okay. And similarly, you have minus x1 less than or equal to 0, lambda 2 x2 equal to 0 and lambda 2 greater than or equal to 0, minus x2 less than or equal to 0, lambda 3, okay, lambda 2 x1, lambda 3 x2 is equal to 0 and lambda 3 greater than or equal to 0, right. All right, yeah. So, I have just copied down these constraints whatever I have boxed here. Okay. So, when you do it for these set of constraints what we have written down here. So, you get one thing that we need to understand is that when you minimize minus x 1 x 2 or maximize x 1 x 2, right. So, this value increases as you increase x 1, right. So, the answer is actually going to lie on this particular line, right, because it cannot lie inside. So, since it is given that lambda 1 into p 1 x 1 plus p 2 x 2 minus w is equal to 0, okay, that is automatically satisfied because p 1 x 1 plus p 2 x 2 minus w is actually equal to 0. Okay. So, let us take that we have p 1 x 1 plus p 2 x 2 equal to w. Okay. So, that is understood. Okay. So, that is because x 1 x 2 is increasing and we are maximizing it, or minus x 1 x 2 is decreasing and we are minimizing it. So, that is going to happen at the highest possible x 1 and x 2 that is available in the given set, right. So, this is known and lambda 1 is greater than or equal to 0. Okay. And we also have the following, we have x 2 is equal to, so when we simplify this we have x 2 equals lambda 1 p 1 minus lambda 2 and x 1 equals lambda 1 p 2 lambda 1 p 2 minus lambda 3, right. So, let us consider the case when lambda 2 equal to lambda 3 equal to 0. Okay. So, in that case we have x 1 and x 2 are greater than 0, right. So, we will have from these two equations. Okay. So, you have x 2 equal to lambda 1 p 1 and x 1 equal to lambda 1 p 2, right. And if you substitute this in this equation p 1 x 1 star plus okay, I will write this. When you substitute this in back into p 1 x 1 star plus p 2 x 2 star equal to w, we have lambda 1 star p 1 p 2 plus lambda 1 star p 1 p 2 equal to w. So, I will write this as substituting on substitution. So, we have this, which means lambda 1 star is w by 2 p 1 p 2. Therefore, x 1 star is this multiplied by p 2, which is w by 2 p 1, and x 2 star is w by 2 p 2. Okay. So, so this is one of the solutions. Okay. So, x 1 star, x 2 star, lambda 1 star, lambda 2 star, lambda 3 star is w by 2 p 1, w by 2 p 2, w by 2 p 1 p 2, 0 and 0. Okay. So, we should also consider cases when lambda 2 star, lambda 3 star are non-zero, that is or exactly positive, since we have these conditions. Okay. So, you can show that I mean solutions do not exist for this problem, doing it for the sake of time. Okay. So, one can show that this is the unique critical point. Okay. And yeah, so if you actually work out the second order conditions, okay, you can see that del 2 L of x lambda is actually, yeah, if you differentiate this with respect to x 1 you have 0, for x 2 you have minus 1, similarly here as well you will have minus 1. So, it is actually 0, minus 1, and 0. Okay. Is that correct? Yes. So, yes, this is correct. Okay. So, that is the Hessian of the Lagrangian. Okay. And yeah, you also need to see what are the active constraints. There is only one active constraint, which is P1 x1 star. So, one active constraint which is P1 x1 star plus P2 x2 star minus W equal to 0. X1 and x2 you can see they are actually greater than 0, right. So, yeah, so if you consider T of x star, it is actually those D for which D1 x1 star plus D2 x2 star is equal to W. Okay. So, if you consider only these D, okay. So, let us see if D transpose del 2 L of x lambda is into D is actually minus 2 D1 D2, okay. But I am sorry, this should be equal to 0. Yeah. So, now we need to find the tangent space. So, recall that the tangent space at x star is D such that D transpose del G I of x star equal to 0. Okay. So, yeah, there is only one G I for which this happens. So, that because there is only one active constraint, and so, it is D such that D transpose P1 P2 equal to 0. Okay. So, it is the set of all D for which D1 P1 plus D2 P2 equal to 0. Okay. Now, let us verify if yeah, T transpose del 2 L of x star lambda star T is, so what is this? So, it is actually minus 2 T1 T2, and so note that it should I mean if D1 P1 plus D2 P2 equal to 0, then we have D2 equals minus D1 P1 by P2. Okay. So, here as well we will have T2 is minus T1 P1 by P2. So, that is 2 T1 squared into P1 by P2, and this is greater than 0 for all T1 positive. Okay. So, yeah, therefore, the unique critical point is also a local minimum. The critical point is a local min. Okay. Yeah. So, you can see I mean how we actually solve constrained optimization problem. Okay. This actually gives you primer on optimization, right. So, when you are actually given either an unconstrained optimization problem where you are minimizing f of x with x ranging over any R n, right, or a constrained optimization problem where you are minimizing f of x subject to x belonging to some particular set. So, that particular set is actually characterized by a set of inequality constraints and a set of equality constraints. Okay. So, whenever this happens, so yeah, I mean the method is as we have described. So, we first find the set of critical points and then we also verify the second order conditions, right. So, this I think should have given you a sufficient primer on optimization. So, the week 1 gets completed here. In the next week, we will actually learn the basics of Python, okay. And after that we will actually learn why solving optimization actually requires the use of a computer, okay. Thank you.